Thank you, Bhumideen, very much for organizing this wonderful workshop, and very happy to be here. So I'm Qianxiao Li, and today I'm going to talk about something that's a bit different in spirit with the rest of the talk up to now. So instead of talking about how machine learning or deep learning can help us do estimation, prediction, and control problems, I'm going to talk about something in the spirit of the reverse direction, which is what can dynamical systems in control theory help us understand certain interesting aspects of deep learning theories of. So here's like the main motivation from a deep learning theory point of view is that I'm sure you have all heard this criticism argument that deep learning is not like alchemy, right? So you take a deep network and you have many hyperparameters and you tune them until it works for your problem. So there's very little, mathematics is actually going on in here. But I want to argue that this is not really an isolated problem. Often, mathematical investigations start this way. And here's one example, right? So this is perhaps the first foray of data science for humankind, right? So people observed that from Earth's viewpoint, okay, for example, the motion of planets, they tend to go this very erratic motion called retrograde motion, right? So if you believe that the Earth is the center, this is a very strange phenomena. And ancient astronomers tried to make models of this, okay, using data. And the first very successful model is due to Ptolemy and other astronomers who built on them. It's basically saying, okay, if I want to model the motion of this planet, what can I do? The simplest model I can do is one circle around this center of the center is the Earth. And of course, this doesn't fit the orbit very well, right? So then, what Ptolemy's idea is that, well, we don't have to stop with one circle. The next simplest thing is two circles. So what we can do is to take the first circle as the orbit of the center of the second circle, and then you have a second circle. And when you fit this radii and the angular velocity well enough, you produce an orbit that's quite similar to what you observe, right? And then you can do that for three circles, and you see that the accuracy improves quite a lot. Now you can see that this is really very similar to what we're doing today, okay, in deep learning. It's pretty much the same thing. But the question is this model alchemy, right? It works really well. And there must be a reason behind why it works well. And fortunately, this is the good news is that we understand why it works well now. So why does it work well? Well, if you look at the following, so instead of looking at in an XY plane, you identify the plane with the complex plane. Okay, then the first circle, center is origin. And on the first circle, you have a circular motion, so z1t, which is this point, is just 0 plus some exponential, right? With some radii, which is the modulus and the angular velocity, which is w1. And then if you want to build another circle on top of it, right, the second circle, then this is just the center of the first circle plus another of these exponentials. And you can see you can keep going and going, and what do you get? Well, you get a Fourier series, a generalized Fourier series of a curve, and we know that for sufficiently smooth curves, they admit this kind of approximation. So in other words, the mathematics behind Ptolemy's alchemy is Fourier analysis, which is something that we really understand very well, okay? So I think this gives us some hope that the reason deep learning succeeds is not arbitrary. There must be some mathematics behind this that we want to understand. Okay, so there's new mathematics. Then the question is, what is new, right? What is new about these deep learning models compared to what we used before, let's say, using combinations, linear combinations of polynomials and so on, or shallow neural networks even? Well, it's in the word deep, okay? So these deep architectures, they are, composed of a composition of many, many layers. They could be convolutional, they could be attention layers like ChatGPT. And also, we have heard a lot of recurrent models today. You can also think of it as a composition of recurrent transformations. So this is what's new. And the question is, what is the mathematics of building complexity out of compositions? And you can see that that's probably related to dynamics, right? So here we want to present a dynamical view of deep learning and try to see what kind of mathematical questions it leads to. So I'm going to consider the simplest case of supervised learning. So you have some input, okay, it's an image or a prompt. And the output is either a label or some reply. Okay, so you can actually do some prompt engineering and make ChatGPT say that. You can try it yourself. Okay, so to learn this relationship in X and Y, input and output, we have to use some hypothesis space. And I'm going to focus on this very, very successful family of hypothesis spaces called deep residual architectures. So here's what's happening. You take an input, and you pass through many, many so-called residual layers, and you get some output features, and then you can apply a simple classification or regression at the end to form your network. So this is basically the template architecture. And each of these residual layers takes the following form, right? So the xt plus 1, which is the hidden state at t plus 1 step, is just xt, this is the residual part, plus some nonlinear transformation, okay? And this nonlinear transformation can take many forms, like fully connected blocks. You see that this is the usual affine transformation and nonlinear activation. You could also have convolutional blocks, and in ChatGPT, this would be like some attention blocks, which is a little bit more complicated. But they're all of this form. Okay. So here's how we can link this to a dynamical system, is that you imagine that there's many, many of these layers, because we really want to study what happens when you compose many layers, right? So let's take that to the extreme and think about what if I just idealize this connection, this residual layers by adding this delta t and taking it to 0 formally. You arrive at an idealized model of deep learning, which is a continuous dynamical system that matches some input signal to some output features on which you can do some classification or regression. And our goal is to understand how this transformation actually helps to build complexity into the model. Okay, so here this theta t will be the weights at each layer, and f will be the architecture of each layer. Okay, so you can see that this is actually very much like, it's exactly the control system. Okay, so the question we want to really study is how does composition, which is now understood as dynamics or controlled dynamics, lead to expressivity in deep learning. Okay, so here's the problem we want to study, is the problem of approximation theory. This is perhaps the simplest problem you can pose when you have a hypothesis space, right? So the idea is that, okay, you have some hypothesis space of some deep residual network space, and you're trying to learn some map, which is a target mapping between x and y. And approximation question basically asks you how small is this approximation error, right? So the first question you can ask is, can the distance here be made arbitrarily small as you increase the size of your hypothesis? And also, how does this distance depend on some complexity of your hypothesis space, your approximation budget, let's say the number of layers, and target, like what kind of targets emit some efficient approximation. Okay, so these are the two interesting questions. Most of the results I'm going to talk about is on the first one, but the second one I'll motivate something as well. Okay, so the question is, okay, now we we have idealized residual network as some sort of flow. Now you may ask, okay, how does flow actually approximate functions? How should we understand its role? Right. So here I give a very simple example where your target function f is some like this norm function. Okay, so these are the level sets, right, circular. And now I have a very simple function that's certainly not a good approximation, which is g. This is just a linear function. Okay. I'm going to attach or compose G with some flow map of some dynamics that I train on this data set and try to see how I can compose G with phi, this flow map, and try to approximate this. Okay, so I'm going to show you the animation, and on the right-hand side, you will see some arrows, which is the trained vector fields or the control vector that is being applied to the system. Okay, so as you can see, as you increase T, slowly, these control signals are rearranging or transforming the domain so that these level sets are being changed and they approximate f in some sense, at least in the average sense. But you can see that it does not change the topology, right? Because these are diffeomorphisms. So you can see that the approximation cannot be cannot really hold uniformly. That's a very important point. Okay. So let's try to understand, so here basically this animation shows the role of the flow is to transform or rearrange the domain appropriately so that the functions match, okay? And it's very different from, let's say, linear combinations of basis functions. Okay, so here's what we're interested in. So we have some control dynamical system, this idealization of your neural network, the deep ones. And you want to study what kind of transformations can the flow maps, that means the map between the initial condition and the terminal condition of this dynamics, what can they approximate, right? So this input feature to output feature map. And understanding this will characterize expressivity of deep networks in the depth direction. Okay, so I think that is one of the new things about deep learning. That's why we're interested in this question. Okay, so how can we formulate this as abstract problem? So we can, first of all, we can do away with explicit parameterization and just introduce this ft, which is your control vector field, which is chosen from some family of vector fields. We call it curly f. So you can think of this curly f as just one way to write all these parametric functions, but we can consider very general curly f. And we call this a control family. So we are basically interested in the size of these attainable maps, which are just all the flow maps that can be represented by a dynamics here, where the right-hand side comes from this family of controls. Okay, so you can see that this aft is directly determined by f, and if you take the union over all possible depths, and that is all the flow maps you can form out of this control family. And the question we want to answer mathematically is, how does f affect the size of AF? Okay, so AF is all the maps you can learn. F is the structure of your network, basically. Okay, so it turns out this is not an entirely new mathematical question. If f is C1, that means if you consider this right-hand side to be a very large class of functions, then some things are known. So the first one is that this attainable maps, they are all orientation preserving, means you can think of it as Jacobian is positive, diffeomorphisms, okay, C1 diffeomorphism. And the second one basically says that the set of diffeomorphisms that can be represented by a flow is very small, okay, is negligible. And the third one says that it is dense in LP. Okay, so in other words, almost no maps can be represented by these flows, but in dimension greater than or equal to 2, they can be approximated by this flow. Okay, so this is what is known. So they are very powerful, but almost nothing can be represented by them. But here in deep learning, we need to think about a more finer question, in the sense that this f is not just like all C1 functions, because you can't parameterize them. Instead, you have a smaller set of controls, and it corresponds to some selection of layer architecture. So for example, in fully connected network, you have a very precise form for f, and this f is certainly not going to represent or even approximate any, not going to approximate C1 functions, right? It's a very small set. So D is finite. So we want to investigate the following mathematical question, which is what properties of F can induce density of AF? Okay, so we know that C1 is enough, but can we do with less? So here's one result in this direction, which gives a set of sufficient conditions on F to induce density. Okay, so basically we need two assumptions. The first one is it is restricted affine invariant, which means that if you give it an offset and a scaling of any control function in your set, you should still stay in your set. Okay, this is certainly true for most, if not all, machine learning architectures. And then the second one says that this closure of the convex hull of F contains a function whose zero set is like a convex set. So basically, you can think of this function as having zero on a bounded convex set, and everywhere else is non-zero. Okay, so I'll show you a picture of it. And you can show that a lot of this popular architectures have this. So as long as you satisfy these two conditions, then this AF is dense in LP over compact sets. Okay, so what is the consequence of this is that it immediately implies the density of finitely wide but infinitely deep or arbitrarily deep neural networks for many, many architectures. You just need to check those two conditions. And certainly for fully connected network, it works. For composite blocks, like if you compose two of these blocks together and then you add a residual connection, sometimes people do that, it also works. And then, of course, fully convolutional networks and other symmetric architectures, you can also adapt the proof to hold in those cases. Okay, so it's basically a very general sufficient condition. Now, we had the assumption that this dimension is greater than or equal to 2. So what happens then when dimension equals to 1? Of course, this is not very important for applications, but it's interesting to ask this question nonetheless. So here, dimension equals to 1, there's a problem because your flows are orientation preserving. So in one dimension means it's increasing. Okay, so it will always parameterize increasing functions. So increasing functions cannot approximate any function that's not increasing, right, or non-decreasing. So we can't hope for it to be dense in LP local in 1D. But it turns out that this is the only obstruction. That means if you only care about increasing functions, then under the same conditions, it will still be dense. Okay, so that's the one-dimensional case. Okay, so I want to say a little bit about proof idea, which links this to controllability. Okay, so the proof idea is basically 2 steps. One is you just take a grid over your compact set, and then you try to shrink all of this mass into some points. Okay, and then you can then match each of these points to the target mapping of your choice. Okay, so you just shift them around. And how do you do that? Remember that I said that we have a function that takes 0 value on some convex domain and non-zero elsewhere. So this one, we call it well function. Okay, so this function. And if you shift this function, so first of all, on this function, you can see that if you use this to drive the dynamics, any points inside here will stay still, right? It won't move. And any points outside of this will start to move. Now, if you shift and translate this function all over the domain by this affine invariance, choose the affine invariance, then you can achieve both this shrinking map and also this point matching map. And then you can show that this one is enough to achieve density. So in some sense, it's like kind of like a partial Stone-Weierstrass kind of theorem for compositional maps instead of algebras. Okay, so here the last step is very much like control, right? So you're mapping points to other points. So the question is, what is the connection between this result and controllability? Okay, so here, let me just remind you, I think many of the audience know exactly what this is. A controllability problem is basically a very related problem. We consider the same kind of control family on some manifold, but just imagine it's RD, okay? And we say that the system is controllable if I give you any initial point and any terminal point, there is a trajectory driven by the control family that maps the initial point to the final point. That's what controllability means, okay? And so what conditions on this control family will guarantee controllability? So this is a very well-studied problem in control theory, one of the major results. So here, I'll just motivate this a little bit. So you can see, okay, what are the directions that I can reach with my control family? So of course, all the vector fields in my control family, that's enough. From x0, I can go into each of the directions in my control family. So this, these directions are all here. But this is not the only ones, because what I can do is from x0, I can use f1 in my control family, f2, and then minus f1 and minus f2. And then you go back to a point that is not really exactly where you started from because these things don't commute, right? And if you calculate this, you basically get this direction is the Lie bracket of these 2 vector fields. And that is also a direction I can reach, right? And then you can see that I don't have to stop here. I can do many more of these Lie bracket operations, and all of it you can reach. So you can define this Lie algebra, which is simply all of these directions that you can generate out of this Lie bracket operation, okay? And a very classical result in differential geometry and control theory basically says that, in the RD version, it just says that if this Lie algebra's direction fill up the entire space locally at every point, then the system is controllable. So in other words, in this room, if this point and all the directions is form a ball, then I'm done. Right? So because it forms a ball at every point, I take some union, I can go from anywhere to anywhere. So this is what is known in control theory. However, this is not quite enough, because if you think about this, it's not really enough for us, for the system to control one point to another point, right? Because we are thinking about approximating functions or doing some classification regression, not of one data point. Maybe of many data points, an infinite number of data points. So for example, in empirical risk minimization, that means minimizing training error, what we need to do is to use the same control to steer some tuples of points. So these are all the training input data, and these are the output features or something. We want to steer this for all n using the same control. This is number one. We have to use the same control to steer many points. So this is like kind of ensemble control problem. But it's also not quite that, because we want to do that for any n. So this control family must be able to do that for every single n. And we call this a universal interpolation property. Okay, it's slightly different from universal approximation. We'll say that later. So this is the universal interpolation property. And you can see that this universal interpolation property, or UIP, is much stronger requirement than controllability, right? We need to control many points using the same control, and we have to do it for arbitrary n. So you can imagine this is not easy to do. However, remember that we use affine invariance a lot. So affine invariance is present in a lot of machine learning architecture. So we define affine invariance by, if your f is in this set, I apply any affine transformation of the following, it still stays within this set. So once you apply this, you assume that your control family has some affine invariance. It turns out that this will essentially enable the UIP. Okay? So more precisely, we can prove the following result, which says that in dimensions greater than or equal to 2, if you assume that your control family is Lipschitz and affine invariance, then you have the UIP if and only if your control family has one nonlinear function. Okay, that means your family has one function with one component being nonlinear, you can make it interpolate arbitrary points by just stacking layers. Okay, in other words, this stacking is really, really powerful. Okay, the proof. Okay, I'll write out what the idea is, and I'll just describe it. You can read it. So the idea is very simple. So we can think about simultaneous control as a control problem in ND dimensions, right? And now we can just go with the kind of a argument just now, right? So imagine this room. If I have universal interpolation that fails in certain dimension at a certain point, then you can see there must be some point where the reachable set is not a ball but lies on the hyperplane. Okay? So if it lies on the hyperplane, then you have a nonlinear function in your control set, you can form some sort of equation that holds for all translations and affine transformations. And now you can take some Fourier transform of this with respect to all your translations, which is B, and you show that the support of the Fourier transform has to be 0. In other words, it's a polynomial, and you assume that your system is nonlinear and Lipschitz, so that's contradiction. All right, so that's basically how you prove it. Okay. Now, to conclude this part, we have two concepts. Right? One is the universal approximation property, which says that can you approximate in LP some map using your flow. And then on the other hand, on a control theoretic kind of approach, there's an interpolation property, which says can you interpolate all of these points? Now, very interesting question is, are these equivalent? All right? Well, it turns out the answer is no. So you can actually come up with counterexamples to show that each of them does not imply the other. So, for example, the approximation does not imply interpolation because the dynamics can have some fixed points, right? So, for example, this dynamics has a fixed point 0. So, in other words, 0 will always be mapped to 0 under this dynamics, but you can always construct the dynamics to be expressive enough so that you can interpolate arbitrary data in R2. And similarly, the interpolation property does not imply approximation because you can construct dynamics that, for example, preserve some phase space volume. So its Jacobian is unit. So therefore, you cannot approximate any flow maps whose Jacobian is not of unit size. Okay, so they're not equal. Then the question is, are there cases where they're equivalent? So why is this an important question? Because we want to see to what extent can we apply this control theoretic thinking, which is more about interpolation of data points, and how can it translate to some results in approximation theory, which is density of some hypothesis space, right? So we want to think about what are the cases where they are actually equivalent. And the idea is basically the following, right? If you think about why interpolation is not enough for approximation, you can think of this polynomial example, right? So if you're interpolating some points sample from this data, and as you sample more, data sample from this curve, as you have more and more data, the interpolation polynomial may get larger and larger oscillations. So if you don't control it, this interpolating sequence might not be an approximating sequence, right? But you can also see that how you can control this very easily is that if you assume that, or if you enforce that, for example, the some Sobolev norm of this interpolant is uniformly bounded, perhaps by some factor of the Sobolev norm of this target, you have uniformity. And then this interpolation approximation will be equivalent. So this we know very well in polynomial approximation, as Runge phenomenon, right? It turns out the same thinking can be applied to a composition, except that we want the uniformity to be in time. In other words, when interpolation and approximation are not equivalent, is precisely when you take longer and longer time to interpolate the points as you have more and more points. And that's when interpolation does not imply approximation. So what we can show is a very rough case, but if you're interested, I can tell you the exact formulation, is that interpolation and approximation are actually equivalent if these points you're trying to interpolate or approximate are sampled from a graph of a function, and the interpolation time is uniformly bounded over all the domain. Okay, so this point is, this also gives you quite an interesting function space to think about, is if your function has this property, then maybe a deep network is a good one. Okay, so this is something that we're still working on. Okay, so finally, with a few minutes, I will talk about the rate of approximation, okay? So UAP, UIP, you can think of them as density results, right? So it says that you can approximate some function if you have sufficiently large network, and you can see from the previous talks that this network can be very large. Now the question is, how can we, what kind of functions are good to approximate? So let me give you one example. In polynomial approximation, we know, of course, the space of polynomials is dense in continuous functions, but this doesn't really tell us exactly which functions we should use polynomials to approximate. So this result due to Jackson shows that if you restrict these polynomials to be of degree at most n, so you can think as with n kind of network, then the approximation error decreases n to the minus r, where r is the smoothness of your target function, and is proportional, the error is proportional to the smoothness, the norm under CR of your target function. So what this result tells you is we should use polynomials to approximate smooth functions, right? So if you have a very smooth target, you should use polynomials. And also vice versa. If your functions are not smooth, you shouldn't use polynomials. Now the question is, what is the corresponding notion of complexity in time of flow approximation? So we want to ask this question because we want to know when should you use a deep network, as opposed to a shallow network, right? What is really deep learning good for? Now we only have very partial results for this. So for example, in one dimension, it's not very interesting in applications, but we can show something that's quite instructive. If you think about your control family being a ReLU network, where you restrict the norms of this weights so that your time scaling is fixed, so the time is meaningful. Then, okay, so don't read the whole thing, just read this line. We show that basically a target function phi is in your hypothesis space up to time t if t is greater than some complexity that depends on the logarithm of the derivative of phi prime. Remember, phi is the increasing function, so you can take a logarithm of its derivative. Okay, so you can see this is quite interesting. So the complexity measure of flow approximation in this case takes the form of the total variation of log of phi prime. Okay, if you compare this with linear approximation theory, usually it's phi's derivative, right, CR. But here, this is very different. In particular, if you look at this under our complexity, the constant function or the zero function has infinite complexity, right? Its complexity here is infinite. Whereas for linear combinations, approximating the zero function is trivial. So something that's very easy for a linear approximation to approximate is very difficult for this approximation space. And on the other hand, the identity function has zero complexity, right? So if phi x equals to x, then this complexity vanishes. So this means that the class for which you can approximate using a deep network well seems to have very different structure to the usual kind of Sobolev or smoothness spaces. Okay, but to completely characterize this is difficult. I should also remark that we also recently shown that this rate is optimal in the sense that if you compute the optimal control of this network, it's also of this complexity. That means that this is the right measure of what functions are easy to approximate. But for general cases, it's much more challenging. So for example, some known results show that if you have a generic target function, when I say generic, I mean you still use kind of Lipschitz class or C1, then your rate in depth will scale basically badly with dimension. So in other words, as dimension increases, you need a very, very long deep network, which is not quite what we observe in practice. So really, the identification of function space is very important. Okay, so let me just conclude. So here we talk about the connection between control theory and deep learning in terms of approximation theory. And you can see that it's really very much related to controllability. What I didn't talk about is the optimization aspect, which is also related to optimal control, as you might suspect. So I'll show you some references. This is really interesting. But there's a relationship, but each of this is a bit different. There's an infinite dimensional twist to it, right? So this control is simultaneous and in all data points. And of course, this optimal control is also in the mean field sense. Okay, so the key, I think, takeaway is that this composition is very powerful in building complexity, but there is a very inherent bias towards what kind of function admits a good representation or approximation. And this is still to be discovered. Okay, finally, I want to say that this kind of structural compatibility also features in sequence modeling. And my student, Shida Wang, is going to present a poster on this. So please have a look. And here are the references. Yeah, and I would like to thank my collaborators. So my student Jingpu Cheng did this work, and my collaborators Zhou Shen and Ting Lin, and the main authors of these works. Okay, thank you very much.